Hi there, and welcome back to 365 Data Science. In today's video, we'll explore the fascinating world of natural language processing, or NLP. We'll cover what natural language processing is, the evolution of NLP techniques, including rule-based systems, statistical NLP, machine learning-led NLP, and neural networks and transformers. We'll also address key concepts like vector embeddings, and finally, we'll look at the impact of recent innovations like large language models. Let's dive in. Natural language processing, more frequently referred to as NLP, is a field of computer science that studies how computers understand, interpret, and generate human language data. NLP came to life around the 1950s. In the early days, the first NLP methods focused on rule-based systems, which used language grammar rules to try to process the text. For instance, in designing such a system, I might establish a rule: treat sentences starting with can you, will you, or is it as questions. Then, when the system processes the sentence, can you help me, it will recognize it as a question. This rule, however, seems quite basic and manual, doesn't it? In the late 1980s, and especially early 90s, statistical NLP emerged, marking a shift from rule-based systems to a probabilistic approach that interprets language data through extensive data analysis. In the 90s, a statistician might have been tasked with designing a program to identify whether can is used as a noun or a verb in a sentence. The difference is very important because, as a verb, can describes a person's ability to do or accomplish something, whereas as a noun, it refers to a container, like a Coca-Cola can. So, back in the 90s, I would have to gather many sentences containing the word can and make annotations whether the word was used as a noun or verb in any of these sentences. This would allow me to perform context analysis by analyzing other words can was used with. For instance, the analysis might reveal that when words like you or I are close to can, it typically indicates a verb. Alternatively, if words like soda are used in the sentence, we most likely have a noun. The final goal of this analysis is to obtain a model capable of indicating the probability of whether can is a verb or a noun in a given sentence based on the frequencies calculated earlier. Attempting to discern patterns in the data in this way seems akin to primitive machine learning, doesn't it? Before we get into recent NLP advancements, I'd like to introduce 365 Data Science's learning platform. If you're excited about AI and machine learning, we've got the perfect courses to get you started. Our Introduction to AI course provides a comprehensive overview of artificial intelligence, while our Machine Learning in Python course offers hands-on experience with popular ML libraries. And if, after watching this video, you're particularly interested in natural language processing, our NLP for AI course teaches you how to leverage Python and machine learning to build effective NLP systems. 365 Data Science has something for everyone. Explore our full range of courses and start your AI and machine learning journey today. Now, let's get back to our discussion about NLP. In the 2000s, NLP experienced a significant boost when statistical analysis made its way to machine learning-led NLP. Vector embeddings were a key facilitator in this process by transforming words and sentences into numerical arrays, effectively capturing the meaning and relationships within the text data. How does this happen? Well, the great thing about vectors is that they can represent more complex types of information, such as text, images, audio, and other types of unstructured data. For example, each word in a sentence can be represented as a vector and stored in a high-dimensional space called vector embedding. When working with AI models, vector embeddings are typically several hundred to thousands of dimensions deep, not just 2 or 3. When working with AI models, vector embeddings are not two-dimensional. They're not three-dimensional, but a few hundred or thousand dimensional. As you can imagine, the meaning of something as complicated as human language can't be captured with one, two, or three-dimensional vectors. Instead, we need hundreds, even thousands of dimensions. The key idea is to use embeddings to store and retrieve data based on semantic similarity. So, text data can be represented through vector embeddings, which serve as a critical enabling factor. Moreover, powerful new ML models emerged, enabling computers to analyze extensive text databases as vector embeddings. These models learned to detect subtle linguistic cues indicating sentiment, like sarcasm or irony, nuances previously elusive to basic statistical methods. The emergence of neural networks in the 2010s revolutionized NLP tasks like translation, speech recognition, and text generation. This is because neural networks, with their deep, multi-layered structures, excel at detecting complex patterns beyond the reach of conventional machine learning methods. Transformer architecture, introduced in 2018, is one of the most recent innovations. It revolutionized the NLP field and led to the creation of large language models. This architecture made the development of LLMs like GPT and Gemini possible. Natural language processing, AI's linguistic ability, is a rapidly evolving field that continues to push the boundaries of what's possible in AI and machine learning. Let's recap the key points we've covered in this video. NLP is a field of AI that enables computers to understand, interpret, and generate human language. It has evolved from rule-based systems to statistical approaches, machine learning-led NLP, and now neural networks and transformers. Vector embeddings play a crucial role in representing text data for AI models. And recently, innovations like transformer architecture have led to the development of powerful large language models. Thank you for watching this video. If you found this content helpful, please like, subscribe, and follow for more on data science, AI, and machine learning. Until next time, keep learning.